This is Jonathan Armstrong with my final presentation for Big Data Analytics at Columbia University, covering the development and analysis of a generative algorithm for universal adversarial perturbations, or UAPs. Basic idea is that it's possible to hack model image classifiers by applying a small amount of noise to that image to induce the classifier to misclassify an image. Universal adversarial perturbations are perturbations that are effective across both images and models. For this presentation, covered a lot of material in this project, so some parts I might have to rush through a little bit. Basically, I'm going to go over generating UAPs, analyzing those UAPs, summarizing that analysis, and using that information to help build a generative algorithm, and then finally analyze that generative algorithm and compare it to the original approach. So since there's no database of UAPs available, I had to build that up from scratch. So what I did is reuse source code available from the authors of the original UAP paper. I used the same model, Inception, and ImageNet validation data, which is about 6 gigabytes, 50K images, and used TensorFlow, which was required for the Inception model. Long story short, took quite a bit of work to get the code stable and running in a way that I was able to run quick enough to generate UAPs. After getting that all working, it took me about 2 weeks of running to generate 44 UAPs. Process was really slow, so I had to stop it sooner than I would have liked. And I can continue on with the rest of the project. So with these 44 UAPs, I could start taking a look at them and figuring out what makes them tick. First thing I did is I looked at the distribution of perturbation values. Specifically, I did that for all 44 UAPs split on the color channels, red, green, and blue. Here you see that the distribution is fairly symmetric and that there's a lot of saturation at the endpoints. That made me ask the question, well, what happens if you fully saturate everything, basically take negative values to -10 and positive values to +10? So I went ahead and made a framework to start evaluating that. I saved 100 preprocessed images to evaluate the fooling rate that resulted from applying different transforms to a given UAP. Baseline fooling rate we're working with for the images I randomly selected is 76%, and the first transform I looked at was saturation. Here you see that saturation increased the fooling rate from 66 to 83, and also notice that it's pretty indistinguishable, the net effects of saturation. So that's a really good approach to improving the effectiveness of a fooling of a UAP. Additionally, what happens if you what is the relationship between features across the color layers? So if I keep one color layer fixed, shift another one, and then shift a third color layer differently, what happens to the fooling rate? Here we see it dropped from 76 to 41, which tells me that the relationship between features across the coloring layers is very important. So what happens if you basically just translate the image? So basically cut it in half and swap those two parts. Here, the fooling rate barely dropped from 76 to 73, which makes a lot of intuitive sense. Basically, the universality of a UAP means that it's more about the textures than targeting any one part of an image. Finally, want to see what happens if you swap color layers. So swap red with green, green with blue, blue with red. Went ahead and did that for a couple different options and got pretty poor fooling rates as a result of that, which means that there are color targeted features that don't generate well for other colors. Summarizing everything here, key takeaway is that I'm going to ignore color rotation. That is, I'm going to, for my algorithm, I'm going to initialize all layers with the same exact random noise and evolve them the same. We're going to see how that works out. Here are some initial failed attempts until I've settled on a final approach based off of two observations. First observation, deep neural networks are able to make very complicated, very organic functions by simply layering and composing simple functions. Additionally, convolutions are a key component of image classification models. So if we mix those two ideas together, what happens if we iteratively apply convolutions to random noise? We combine that with the analysis from before. So we're going to initialize each color layer exactly the same and develop a convolution layer that's balanced so that the net effect is we're going to have statistically symmetrical result at the end of the day. So after playing around with a few different options, here's what I settled with. Tested it on 100 images and got an average fooling rate that was greater than 50%, which is awesome. So at this point, here's a sample of what some of the UAP textures look like generated with this generative algorithm. Additionally, here's what the random noise looks like as it's convolved over 45 iterations. Also going to go ahead and do a live demo. Right now this is building a UAP according to my algorithm. Key point here is this takes seconds compared to the hours and hours and hours it took to make the other ones I took a look at. Alright, so here is what we've got. Here's what was generated. And we can also see how that evolved over the convolution iterations. Going back to the presentation. So what I did ultimately is generate 50 UAPs using this new generative algorithm, and also incorporated the previous 44 to facilitate comparison, and evaluated all 94 UAPs against the 50,000 images in the validation set, and saved those results to a Google Cloud BigQuery table where I could use Django and D3 to generate plots and help with visualization. Key takeaway is across all 50K images, my 50 UAPs were able to get an average fooling rate of 44.75. If you compare this to the results of the original paper here, you see that on the off-diagonal values, which correspond to UAPs trained on one model and tested it against another, that 44.75 is definitely in the hunt of all these other ones. So I consider that a really big success of this approach. Here we see the ranked fooling rate of each individual UAP I generated, from about 15% fooling rate to 66% fooling rate. I generated some other figures, but we don't really have much time to go through them. There's more discussion in the paper. I'm going to go ahead and finish this with a demo of the website. So what's going to happen is we're loading a random image, which is a wallaby, which good on the model for telling that. Here's the random UAP that I generated, one of the 50. And after applying that perturbation, the model thinks, oh, that's an armadillo. So successful fooling here using one of the better performing UAPs with 65% fooling rate approximately. This is the end of my presentation. I hope you have a great holiday. Thank you for lessons.